Let's try to find out what the answer is to this question now. What we'd like to do is view this problem in terms that we've already discussed in the past. So we decide on a system, and here it's basically just the 8-ball. And what we'd like to do is find out what happens to the 8-ball during the collision. That means writing down exactly what the momentum is initially, and the 8-ball is static or stationary to begin with. So the momentum initially is 0. The final momentum is non-zero. We don't know exactly what value it has, but we can see that it's non-zero. That means that the change in momentum during this process or during the collision is not zero, which of course means that the momentum itself is not constant during the collision. So B is the correct answer. Now we could go through these other options and think about them a bit. C says the momentum is constant only if the collision is elastic. But these two concepts are separate. So constancy of momentum during a collision is a separate issue from whether or not the collision is elastic or inelastic. That last term, of course, refers to what happens to kinetic energy during the collision. And D as well. And of course, E says, is it constant only? It's constant only if the collision is perfectly inelastic. So again, we're trying to link up in these questions the condition on constancy of momentum with what happens to kinetic energy during the collision, and those two things are separate. Let's try now to go a little bit deeper into the question about when momentum happens to be constant during some interaction. This first equation here is a relationship between the impulse delivered to a system and the change in momentum of the system. So recall that the impulse is related to a force in a very precise way, which we'll see in a minute again. And again, what we're looking for are conditions under which the change in momentum must be zero, which is of course the same as the condition that momentum is constant during some interaction. Let's look at this particular condition. So we recall that Newton's second law says that the sum of the forces equals mass times acceleration. But let's just look at the left-hand side of that and look at the sum of the forces in a particular interaction, and let's say that that sum equals 0. Well, here we're going to show, of course, that this implies something about the change in momentum. For example, if we write down the sum of all the impulses delivered to a system, which is really what the net impulse is, and then express it in terms of its basic definition. So an impulse delivered to the system by a particular force is then given by the time integral of that force. So the integral of that force over the time which it acts upon an object. And then since we're summing over all impulses, then a summation comes into play. And all we've done here is swap out the order of integration and summation. That allows us, of course, to take this initial assumption here and substitute it into this position here. And then that tells us that the sum of the impulses is 0, if this condition is true. And then that then leads to change in momentum of the system being 0, which we get from this impulse momentum theorem. Okay, so one condition for the constancy of momentum through a process is that all the forces involved sum up to be 0. Well, that's an exact statement, but we can also make approximations. So if we recall, essentially if we replace forces by the average of forces, then integration actually becomes something where we're really summing over forces times, of course, some time interval. So the mathematics is easier, it works under certain conditions, but where it's very useful is in the particular case when the time interval over which these forces act is really, really small. So if the time interval is short enough, and provided, of course, that the sum of the forces involved is not too large, then the left-hand side of this particular equation here becomes very, very small. In other words, the change in momentum of the system then will be very, very close to zero. So that's an approximate answer, but often approximations in physics, if they're done correctly or applied correctly, are very, very useful. Now let's look at this other question. So we consider an elastic collision. Um, and this is defined really as a particular situation where the kinetic energy is very, very close to being constant throughout the process. So in other words, kinetic energy stays constant throughout some particular interaction, or very close to that. The question here then is to classify the following as collisions. Um, I'm sorry, to classify these collisions as approximately elastic collisions, inelastic collisions, or maybe they cannot be even classified as collisions at all. So let's look at all these four options, or sorry, four scenarios. So number one, two billiard balls colliding. Number two, a satellite slingshot around a planet. Three, a car crash. And four, an object exploding into three fragments. So take a moment again and think this over, and we'll come back and answer it.